We are now considering matchings in bipartite graph. And there is another natural parameter which is closely related to the matching number. So we define a vertex cover is a set of vertices having at least one endpoint of every edge. So we want to find the set of vertices which are incident with every edge. And we write down as the minimum size of a vertex cover. We denote it by beta. So you have a graph. And what was the matching? Matching, you want to find as many as possible to cover all the vertices. And you wanted to use edges to cover vertex. But here you want to flip the relation. You want to use vertex to cover the edges. But before, here the goal was to maximize the number of edges in certain sense. But here, we want to be as efficient as possible, so that we want to choose small number of vertices so that it's incident with every possible edge. Then it's natural to find the relationship between these two parameters, alpha prime and beta. In fact, I mean, this relation is obvious. Why? If you have a matching, then what happens? No matter which vertex you take, so in order to get the vertex cover, your vertex cover has to be incident with every edge. Not only, I mean, so every edge of G. That means it also have to be incident with every edge in any matching. In here, what? You have to choose at least one vertex out of these two to be incident with this edge. And again, at least one out of these two, and then at least one, at least one, at least one. So your vertex cover must have at least 5 vertices here. So in general, at least as many as the number of edges in your maximum matching. You kind of see the intuitive reason why. So in vertex cover, in order to be efficient, your vertex has to cover many edges. So these edges have to be pairwise incident at here. But the matchings are the ones, they are pairwise not incident. So this is kind of your obstacle for being efficient. So if there are large size matching, it's making your job for vertex covering not efficient. Also, I mean, another intuition is that if you have a vertex cover, and then all the edges are between here and then inside of here. So this is an independent set. And no matter which edge you take, it's eating up one vertex from the vertex cover. So your maximum matching cannot be larger than the size of this vertex cover. So that's another intuition why this holds. But again, we have this obvious inequality. But the following theorem by Koenig and Atterbury says that if G is bipartite graph, then this alpha prime of G and beta of G are same. It's not just inequality on one side, same. So as we mentioned, this is obvious. So we want to show the other direction. But what do we know? We already have an efficient tool to compute this alpha prime. By this corollary, by the previous corollary, what do we know? There exists a subset T of X such that this alpha of G is same as X minus T plus N of T. So you have X, then you have this T, then neighbor of T. You take the difference between these two, T minus N of T, and then you take, you subtract from X. So this, out of all choice of T, you find the ones which minimize this. Then you have this equality with that specific choice T, which minimize the expression. But what do we know? You have this T, and you have X minus T outside, and you have N of T, and here. So all the edges are between here, and then here and here, here and here. There are no edges between these two, because that's the definition of neighborhood of T. It's taking every vertex which has neighbor in here. So outside here, there are no edges. In this situation, you can see that every edge is incident with this. So this N of T union with X minus T, this is actually a vertex cover. What do we get? The minimum size of the vertex cover is, not bigger than this vertex cover, which has size N over T plus X minus T, which is alpha prime of G. So this inequality and this inequality give you the desired equality. So we have this Koenig's theorem. Okay. So we have this alpha and alpha prime, which is independence number, and then this matching number. And beta is vertex cover number. And then natural question is there a beta prime? Indeed, we have the following concept of edge cover. We say the edge cover of G is a set of edges that cover all vertices of G. And we use beta prime of G to denote the minimum size of an edge cover. There are one catch here. We have to consider only graphs with no isolated vertices for this concept. If there is a isolated vertex, and there is no way that you can cover this vertex by using any edges, right? So assuming that we define this beta prime. So what we have proved is that for bipartite graph, this alpha prime is beta equality holds. Then question is that do we have the similar equality for alpha and beta prime in bipartite graph? Indeed, I mean, we can prove this, and we will prove this by showing these two statements. First, let's consider this lemma. If you have an vertex graph G, and we have a vertex subset S, then this is an independent set if and only if its complement is a vertex cover. This is a pretty easy statement, and it implies that alpha of G plus beta of G is N. Because what? If this is true, and you take the maximum independent set, then which is complement is vertex cover, and you take the minimum vertex cover, whose complement is independent set, and maximizing one is same as minimizing the other, so we get this equality. Okay, the proof of this is, I mean, pretty straightforward, so I will leave this as an exercise to you. You can check for yourself. And in order to prove this equality, we only have to prove the following theorem by Galai. If G is on n vertex graph with two isolated vertices, then alpha prime of G plus beta prime of G is also n. So let's prove this. We first prove beta prime of G is at most n minus alpha prime of G. Let's prove this first. And what do we have to construct? So again, edge cover is minimum parameter. So we want to minimize the size of edge cover. So it is enough to construct one edge cover of size n minus alpha prime of G. So take a maximum matching M. In G. And you have a M here, and then there could be some vertices outside, and there could be edges between them. But one thing for sure is that there are no edges between here. If there is edge here, then we might add here to obtain a bigger matching. Then what do we have? For each, so we want to find the edge cover, which covers every vertex. But if your vertex is outside of this M, which are vertices not covered by M, and if each edge what we do is we add it to, let's say we take one edge incident to it. For this vertex, let's say you take one edge. And for this vertex, you take a one edge. For this vertex, you take one edge. For this vertex, you take one edge. For this, you take one. For this, you take one. So you do that. So remember, we are constructing an edge cover. So you do this. And what? This uses how many edges? For each vertex, you use each edge. So and we add them, say, to M. And also we take the edges in the maximum match. Then what do we get? Then this covers all the vertices. This is an edge cover. Then how many edges do we have? It has the number of edges in here is that you take a size of M plus the number of vertices outside is M minus 2 of M, size of M. So number of vertices here. And for each one of them, you add on one edge. So this is what you get. This is N minus M, which is N minus alpha prime of G, because M is the largest matching. So this is an edge cover. So it implies that the minimum edge cover has to have the size and most this size of this edge cover. So you get this inequality. And we now prove the other inequality. And this can be rearranged that this is alpha prime and then this is beta prime. So we want to prove this. So again, what do? We want to construct a matching of size, say this. So take a smallest edge cover, say L. Then we can actually try to consider how it looks like. How does L look like if you have a smallest edge cover? One thing we know is that if you have a vertex here and a vertex here, and this edge is in L, this edge is in L, then we don't have to add this edge to L at all, because this vertex is already covered by this edge. This vertex is already covered by this edge. So there is no point of adding this edge to L. So if both endpoints of an HE is already in L, line other edges in L, then what? L minus E is a smaller edge cover. This is a contradiction. Hence, each component of L. So you take L and then you take the connected component. This has at most one vertex of width, say, degree larger than 1. Why? If you have a component, then between every vertex, you have a path, right? If this has degree bigger than or equal to 2, and this has degree bigger than or equal to 2, you take a path between them. Then what happened? This path could have a length 1. Then any consecutive vertices between them are on the paths. So it's either end vertices which has degree 2, or the vertices inside of this path has degree at least 2 because it's incident with 2 edges. So there are two consecutive vertices with degree 2 in L. Then what? You just delete one. Then it's still an edge cover. So this doesn't happen. That means each component has at most one vertex of degree larger than 1. Then how does it look like? You have a one vertex with degree larger than 1, possibly larger than 1, and everyone else is degree 1. So it's either like this, so star. So so it is a star. So if there are k such stars, so this is disjoint union of stars, so we know its structure, so we can actually get the information on the matching from here. If there are k such stars, then what? This L has n minus k edges. Why? Every 4 vertices it uses, you have 3 edges. Every 2 vertices, you have 1 edge. So every time you have a component, you have 1 less edge than the number of vertices. So we have this because like L has 1 edge for each vertex except the center of the stars. So if we have this star, then you take 1 as center, 1 as the leaf. So the number of edges is 1 for each leaf. So we have that. So what do we know? As k is n minus L, and this k provides us matching of size k. How? We choose 1 edge from each star. This yields matching of size k, which is n minus L, which is n minus beta prime of G, because L was the minimum edge cover. So this is give you a matching, and then alpha prime is the size of maximum matching. So we get this inequality as desired. So these two together proves the theorem that this inequality holds. And together with this and this, and this, these three, wait, did I delete something? Yeah. These three together implies this, as we wanted to prove. Okay, so in this lecture, and the previous video and this video, we proved the Hall's theorem and Koenig's Etherbury theorem, which give us some tools to compute the size of maximum matching in a given bipartite graph. And in next video, we will talk about the matchings in more general graph. If we have a general non-bipartite graph, what can we say about its matching number? It's more complicated than the bipartite case, but we will have some tools that we can exploit. Okay, thank you for listening. I will see you in next video.